2 weeks from the Autonomi 2.0 launch, the development team is executing a pivot away from unproofable Web3 marketing promises to focus on verifiable engineering milestones. As part of this shift, the project is officially removing the permanent data guarantee from its core technical documentation. The mathematical reality is that incentive structures designed for eternal data persistence cannot be proven. No protocol can provide a rigorous mathematical proof for a promise of forever. The new proposition centers on a defensible claim. Data persists for the life of the network, provided it remains immutable, encrypted, and distributed. Ensuring that network survives requires abandoning complex financial instruments in favor of solving technical bottlenecks across 3 distinct layers of the protocol stack. Building decentralized architecture from the physical hardware layer up provides the pragmatic security that theoretical guarantees lack. The first foundational layer of the stack is physical connectivity. The system is designed to leverage existing home computers as global infrastructure. Standard home network routers utilize NAT, or network address translation, to map multiple local devices to a single public IP address. For security, these routers are configured to block all unsolicited inbound traffic from the external internet. While users could manually configure ports, requiring complex router setup prevents a decentralized network from reaching a global audience. The solution is automated, QUIC-based NAT hole punching. QUIC is a transport layer network protocol designed for low latency, securely encrypted connections. This shows the hole punching mechanism. When an internal node initiates an outbound QUIC connection to an external cloud node, it creates a temporary firewall opening. The cloud node then uses that specific path to establish a bidirectional tunnel. Empirical data proves this works. A home node maintained 43 consecutive successful uploads with 0 failures. These stable bidirectional connections easily handle distributed hash table queries, complex pricing quotes, and the transfer of data chunks. Solving automated NAT traversal allows standard home broadband connections to participate directly as nodes in global infrastructure. Physical connectivity is only useful if the network nodes can actually agree on how to route data between one another. The current engineering priority is DHT convergence. A distributed hash table is a decentralized system for mapping data to the specific nodes responsible for storing it. For data to move accurately, every actor on the network must mathematically agree on which nodes are closest to any given address. Here, different nodes hold conflicting address tables, causing the data chunk to fail to reach its destination. Without absolute routing agreement, the decentralized payment system cannot confirm that a node has successfully stored a chunk, which prevents the transaction from completing. Testing on 100-node networks showed that routing tables were not converging reliably enough to support the launch of a public network. One approach currently in development involves optimizing the existing DHT implementation to increase the speed and reliability of table synchronization. In parallel, the team is building custom routing logic specifically designed for Autonomi's trust and data replication requirements. Achieving reliable DHT convergence is the critical path item that determines the launch timeline. Once the network is connected and routed, it requires an economic model to regulate data storage and incentivize node operators. The previous economic model attempted to measure the raw storage capacity of every node on the network. Raw storage capacity proved to be mathematically unmeasurable in a trustless environment, as nodes could easily misreport their hardware specs to game the system. The redesigned model uses a node fullness metric, where pricing is determined by how much actual data is stored relative to its current limits. This creates a self-regulating loop. As a specific node fills with data, the price to store new information on that node automatically increases. These rising local prices create an immediate economic incentive for new node operators to join the network in that specific area. The influx of new capacity causes the local price to drop back to a baseline level, organically balancing supply and demand. This system functions without the need for external price oracles or centralized fee extraction. To effectively manage total supply, a small percentage of every single payment on the network is permanently burned. This burn mechanism creates a deflationary pressure on the total token supply as the volume of data on the network increases. These hyperlocal metrics allow the network economy to self-regulate without centralized oversight. The Autonomi 2.0 stack is now a cohesive architecture where quick hole punching handles the hardware, DHT convergence manages the topology, and the fullness model drives the economy. The entire codebase is being consolidated into a single CLI, or command line interface tool, managed by the With Autonomi organization. It handles everything from file uploads to node management and binary signing, streamlining the workflow for node operators. On top of this infrastructure sits X0X, an agent-to-agent network designed for decentralized collaboration. The X0X GUI, or graphical user interface, provides functional tools for project management, messaging, and peer-to-peer disk sharing. An integrated swarm dispatch system allows autonomous AI agents to post tasks and claim work across the global network. Once an agent completes a task and passes evaluation, a payment in ANT, the network's native token, is automatically triggered through the underlying economic layer. Real-world testing on the live network has already demonstrated successful cross-continent messaging and automated node installations through simple one-line commands. The Autonomi 2.0 update demonstrates that decentralized web infrastructure scales by resolving these specific engineering constraints at the core protocol level.